In our previous video with matrices, we had looked at some operations with matrices, such as addition, subtraction, and multiplication, both with scalars or between two matrices. When we were looking at multiplying matrices together, we learned that matrix multiplication is not commutative. In other words, you can't rely on switching the order of the multiplication and getting the same result. It can happen, it's just you can't rely on it because it won't always, a lot of times it won't happen. But we did find out that matrix multiplication satisfies the associative and distributive properties. At least that worked. So we're going to kind of continue with that thread today as we talk about matrix inverses. Matrices have identity and inverse elements, and we're going to talk about both of those situations. Okay. We know that, like, for real numbers, we can take some real number a and times it by 1 and get a back. Or you could do 1 time, you could switch it because it's commutative, yay. For real numbers, you can do that for any real number a. So you can take a, multiply by 1 and get back the same result. With matrices, it's the same idea. You can if there is a multiplicative identity matrix, I, yeah, we'll go ahead and call it capital I, such that matrix A times I equals A, and I times matrix A equals A. So in other words, you can take this identity matrix, you can either take the matrix times the identity, or you can take the identity times the matrix, and you'll get back just that same matrix for any matrix A. Then A and I must be square matrices of the same dimension. They have to be square matrices for this to work, and they have to be the same dimension, like both be 2 by 2 or both be 3 by 3. So that matrix capital I serves in the same way as the 1 for real numbers. It's that it's the identity, like in the 1 is an identity element in real numbers. The I is an identity matrix in the set of matrices. And in order for this to happen, and if it does happen, then both your matrix and your identity matrix have to both be square matrices of the same dimension. If we're talking just 2 by 2 matrix, it'll look kind of familiar. You could say I sub 2. It'll look like this. Your identity matrix is going to have the main diagonal be 1s and everything above and below it be 0s. In fact, if you're doing like n by n, the identity matrix for an n by n matrix, you're going to have 1 with 0s underneath. Then you're going to have that diagonal. So you just keep going down. So yeah, that main diagonal is going to have 1s. Everything else will be 0s. So a sub I j is 1. when I equals j. So that's the diagonal elements. And a sub ij is 0 otherwise. All right. Well, let's show that we have an identity matrix in an example. Let's say that we have matrix B. It's a, well, you know what? I was going to start with matrix 1, so we can still call it matrix B. I'm just thinking about trying to prove that we have an identity. Let's say we have matrix B. That's 5, 7, 2, and 3. The identity matrix would be 1, 0, or why did I do that? I meant to write it there. You'd have that diagonal of 1s and then the 0s elsewhere. So if you go ahead and multiply B and I together, you'll have 5 plus 0 is 5, 0 plus 7 is 7, 2 plus 0 is 2, and then 0 plus 3 is 3. So the B, and then when you multiply B and I together, you get back the same matrix as you had with B. That's what happens when you multiply by that identity matrix. Okay. Looking at an example that I had worked out here, but I'm not so sure I'm going to use it, so I'm changing my mind. Okay. Let's talk about inverses next. So we talked about identity matrix with the diagonal of 1s and the 0s otherwise. So so I'm going to go on now and get into inverses. Multiplicative inverses. Let's say you have, like, for real numbers, for non-zero real A. You have a multiplicative inverse 1 over A. And you can take a non-zero real number times its multiplicative inverse, and you'll get 1. So you get that identity element back when you multiply them together. So that, we talked about the identity matrix, how you could take a matrix times its identity matrix and get back basically the same matrix. But now we're talking about inverses. Like for real numbers, you take a number times its inverse, the 1 over the number, as long as the number's not 0, and that'll get you back 1, the identity element. Okay, so for matrices, let's say you have A, which is an n by n, square matrix. The multiplicative inverse is written like capital A with a little -1 exponent. Now, up here with real numbers, 1 over A could be written as A to the -1. But with matrices, this is not the same. 1 over A is not the same thing. And in the multiplicative inverse for matrices is not, you cannot write it as 1 over the matrix. It's something different. That would be something else entirely. So anyways, just a little note there. But the A to the -1, so the inverse must satisfy both of these following things. you could take the matrix times that multiplicative inverse and get back the identity matrix. And you can take the inverse times the original matrix, get back the identity matrix. So in this case, it does end up being commutative, but it's a very specific case, so we can't generalize that multiplication is commutative, but it does end up being commutative in that you can take a matrix times its inverse or the inverse times the matrix and get back the identity, that nice identity matrix that we learned about a minute ago. Only a square matrix can have a multiplicative inverse. By the nature of how all this works. So just be aware of that. All right, so how do we find? Well, let's say you have the matrix 5, 7, 2, 3, and you want to find its inverse. Well, you need to be able to take that matrix times whatever the inverse is and get that identity matrix. So since it's a 2 by 2, the identity matrix would be 1, 0, 0, 1. So we have to figure out like what exactly would go in that other 2 by 2 matrix next to it to multiply and get back that identity matrix. All right, so we're going to do a little algebra. We're going to put an x, y, z, w in here, and we're going to find them. We're going to solve for it. So we're going to multiply the two matrices. Okay, so row 1 times column 1 will give me 5x plus 7z. Row 1 times column 2 will give me 5y plus 7w. I already know it has to equal this. Row 2, column 1 would give me 2x plus 3z. Row 2, column 2 would give me 2y plus 3w. All right, so we know that on the left side, the element in a sub 1, 1 has to equal, on the right side, the element in a sub 1, 1. So 5x plus 7z has to equal 1. We know that the element in a sub 1, 2, which is 5y plus 7w, has to equal the other element in a sub 1, 2, which is 0. 2x plus 3z has to equal 0. 2y plus 3w has to equal 1. So we got to solve that. So we now have a system, actually two systems, of equations to solve. One system to solve for x and z, another system to solve for y and w. Now honestly at this point, if you want to use whatever method, you're more than welcome. Like you can use substitution, elimination, graphing, or whatever floats your boat. I'm going to go ahead and use matrices since that's kind of what we're doing here. I'm going to go through and solve this using matrices. So I'm going to go ahead and take that first system and put it into the matrix format here. And I'm going to take the second system and do the same thing. And I could individually solve these systems in these matrices, but we lucked out, and if you notice, the coefficients, like the elements there on that left part, are the same. So we could actually combine into one matrix and then solve from there. We can have the 5, 7, 2, and 3. And then over here, we can put 1, 0, 0, 1. We'll just put it into one matrix and then work on solving. All right, when I solve this, my goal is on the left side to have the 1, 0, 0, 1. And once I finish transforming it so that that happens, the right side will have my solutions. The right side will have my X, Y, Z, and W for me, which will be nice. Yeah, it'll be my X, Y, Z, and W over here. Okay, so when I did this, I felt like it would be easier to swap row 1 and row 2. So I put 2, 3, 0, 1 up top, and then I put 5, 7, 1, 0. Because then I was like, oh, I'll just divide top by 2. So I got 1, 3 halves, 0, 1 half. I didn't end up avoiding fractions. Sometimes that happens. Sorry. Then I did first row by -5 and then added that to the second row. So first row stayed the same for now because I'm just trying to get a 0 underneath that 1. Oh, sorry, that's not going to be a 1, 0 anymore. Oh, why did I do that? Okay. So I did a -5 times that first row plus the second row. So -5 plus 5 is 0. Then I have -15 halves plus 7, which would be 14 halves. So that comes out to -1 half. Then I have 0 plus 1 is 1. Then -5 halves plus 0 is actually -5 halves. Sorry about that. And sometimes I get carried away writing stuff and go, oops. Okay, so I have that matrix now. Slowly getting there. My next goal will be to take that bottom row and get a 1 where I need it. So I'll just multiply that bottom row through by a -2, and that'll get me what I need there. Okay, moving on to the next slide. So top row will stay the same. And when I multiply that bottom row by -2, I got 0, 1, -2, and 5. And then finally, I definitely need that 0 up there. So I multiplied the second row by -3 halves and then added that to the first row. So the second row stayed the same. I have 0 plus 1 is 1. -3 halves plus 3 halves is 0. -3 halves times -2 gave me 3 plus 0 gives me 3. And then -3 halves times 5 is -15 halves plus 1 half is -14 halves or -7. And there we go. Now that I've got the left side down to 1, 0, 0, 1, the right side gives me my solutions. That I need. So that inverse matrix is 3, -7, -2, 5. And earlier, I had already kind of told you that when you took the matrix with 5, 7, 2, 3 and multiplied it by this inverse, 3, -7, -2, 5, you get the identity matrix with the 1, 0, 0, 1. So that's how that works. That's how you find it. Now, if you want to, confirm or verify that two matrices are inverses of each other, it's sufficient to just do like A times B and show that that comes back as the identity matrix. You don't have to also go back and show B times A. That's something to confirm. That two n by n matrices A and B are inverses of each other. It is sufficient to show A, B equals the identity matrix. Not necessary to also show B times A equals identity matrix. It will, but not necessary to show it. Once you show one, then that's proof enough. All right, how about that was some 2 by 2 examples. How about we step it up a little bit and do a 3 by 3? All right, let's say that we have matrix B that has elements. Row 1 has -4, 2, 0. Row 2 has 1, -1, 2. Row 3 has 0, 1, 4. And we want to find the inverse matrix. Okay, so we know that we want to set this up with the original matrix. We're doing an augmented matrix. So we're going to put the original here, do the little bar. Then on the other side, we also need a 3 by 3, but we need that diagonal of 1s with 0s. And then we're going to work on transforming this lovely augmented matrix so that the left side has the diagonal of 1s with 0s. And the right side will tell us what our inverse matrix looks like. Okay, so when I did this, I recognized that the second row has a 1 at the beginning. So I went ahead and switched that up to the first row. You have to carry everything with you. And I also noticed that the third row had a 0, 1. So I was like, oh, that's convenient. That'll help me in my second row. So I moved that up there. And then my first row became my third row. I mean, you might not do it this way, and that's fine. There's all kinds of ways to do it. But that's what I spotted, so that's where I started. Okay, what did I do next? Well, next I worked on getting that 0 in row 3, column 1. So I took row 1 and multiplied by 4 and then added that to row 3. So rows 1 and 2 right now are staying the same. It's so easy to make a transcription error, so you'll hear me pause every once in a while, and basically what I'm doing is going back and like double checking that I copied things correctly or multiplied correctly, because it's so easy to make mistakes. All right, so 4 times row 1 plus row 3. I'll have 4 plus -4 is 0. -4 plus 2 is -2. 8 plus 0 is 8. 0 plus 1 is 1. 4 plus 0 is 4. 0 plus 0 is 0. All right, we're getting there. Next, I worried about getting a 0 in row 3, column 2. So I must have taken row 2 and multiplied that by 2 and then added it to row 3. So for now, row 1 is staying the same. Row 2 is actually staying the same. I'm just going to be using a multiple of it to add to row 3. So 2 times 0 is 0 plus 0 is 0. 2 times 1 is 2 plus -2 is 0. 2 times 4 is 8 plus 8 is 16. 2 times 0 is 0 plus 1 is 1. 2 times 0 is 0 plus 4 is 4. 2 times 1 is 2 plus 0 is 2. And this, so far I've managed to avoid fractions, yay. But this is where it gets kind of sticky. I went ahead and did 1/16 of row 3 so that I could get the 1 down there in row 3, column 3. So now it's going to introduce some fractions. And unfortunately, the result has fractions in it, so I really can't avoid fractions as much as I'd like to. All right, so when I did that, row 1 stayed the same. and row 2 stayed the same. So I was working on trying to get row 3 finished. So I took row 3 and did 1/16. So zeros and 0 will stay the same. 16 divided by 16 is 1. Then I had a 1, so now I have 1/16. I had a 4, which turned into 4/16. You know, honestly, I'm wondering, it's technically 1/4, but it might be worth keeping it as 16ths for now. And then 2/16 for here, because I had a 2, so times 1/16. I know it reduces to 1/8. I'll worry about reducing it later, because I might need it in 16s in order to do some combining and stuff later. So we'll see. All right, then I worked on getting a 0 in row 2, column 3. So I took row 3, multiplied by -4, and then added that to row 2. So row 1 stayed the same. Row 3 actually stayed the same as far as what's happening here in the matrix. But row 2, that's the one that's getting transformed now. 0 plus 0 is 0. 0 plus 1 is 1. -4 plus 4 is 0. And then that should be -4/16. That's going to be -16/16 or -1. I could probably just go and put -1. And then -8/16, which I know is a -1/2, but I'll sleep, or, oh, hold on, -8/16. Oh, sorry, -8/16 plus 16/16 is +8/16. Sorry about that. I'm adding it to a 1. In my head, I added it to 0. All right. Now to get those zeros where I need them in row 1. I need them in row 1, column 2, and row 1, column 3. I think I tackled row 1, column 2 first. So I just took row 2 plus row 1. So for that, okay, row 3 stayed the same completely for now. And technically row 2 stayed the same also. It's where I need it. I'm using it, but I'm not changing the row itself. Okay, so then if you add row 2 and row 1, 0 plus 1 is 1. 1 plus -1 is 0. 0 plus 2 is 2. And you get -4/16, and you get 0, and you get 8/16 there. Then finally, I took row 3 times -2 and added that to row 1. So row 3 right now is the same. Row 2 is the same. Row 1, 0 plus 1 is 1, 0 plus 0 is 0, -2 plus 2 is 0, -2/16 plus -4/16 is -6/16, -8/16 plus 0 is -8/16, and -4/16 plus 8/16 is 4/16. All right, and let me rewrite that so with everything reduced. It's probably bugging some of y'all. We have what? -3/8, -1/2, 1/4. We have -1/4, -1, 1/2. Then we have 1/16, 1/4, and 1/8. All right, so that inverse matrix for B is that matrix with -3/8, -1/2, 1/4, -1/4, -1, 1/2, 1/16, 1/4, 1/8. That is our inverse. We did all that transforming. Now let's confirm. Let's take B and multiply it with its inverse and see what we get. So B originally was much prettier, no fractions. -4, 2, 0, 1, -1, 2, 0, 1, 4. And let's multiply it with that fraction craziness. I don't know if you hear the voices in the background, but my son and my husband are both very loud. I'm in far room of the apartment with the door closed and you can still hear them. But anyways. All right. So if I multiply row 1 and column 1 together and add them up, I have what? 12 eighths minus 2 fourths, which is minus 4 eighths. So -16 eighths or -2. I'm trying to do this in my head. This is so much fun. I need to slow down. All right. Positive 12 eighths. -4 times -3 eighths is positive 12 eighths. Then minus 2 fourths, so minus 4 eighths. So that's 8 eighths, which is 1, plus 0 is 1. All right. And that's what we expect. We should get a 1 up in that corner. Row 1, column 2, I have 2, minus 2 is 0, plus 0 is 0. Row 1, column 3, -1 plus 1 is 0, plus 0 is 0. We're expecting to get the identity matrix here. Okay, row 2, column 1, -3 eighths plus 1 fourth, or plus 2 eighths. That's a -1 eighth. Plus 1 eighth, 2 sixteenths or 1 eighth is 0. Row 2, column 2, -1/2 plus 1 is 1/2. Then plus 2 fourths or 1/2 is 1. Row 2, column 3, 1/4 minus 1/2 is a -1/4. Plus 1/4 is 0. Row 3, column 1, 0. Minus 1/4 plus 1/4, 0. Row 3, column 2, 0. -1 plus 1, 0. Row 3, column 3, 0. 1/2 plus 4 eighths, or 1/2 is 1. Yep, that's what we expected. That's what should happen. Woohoo! So we've been doing it. We learned about identity matrix. We learned about an inverse. We learned about how to find the inverse. We learned that if you multiply the matrix with its inverse, you get back the identity matrix. Now just one weird situation of what if there's no inverse? How do we know that a situation doesn't have an inverse? What if that pops up? Because you know that stuff like that happens. Let's say you have matrix A. It's 3 by 3 with 4, -2, 5, with 0, 1, 0, and with -8, 4, -10. And you want to figure out what the inverse is. So at first, you don't, like, you're going to have to pretend you don't know that there's no inverse because you just asked find the inverse. So let's see what happens so that you can be like, oh, wait a minute, this is not working for me. There's nothing you did wrong. It's just some matrices don't have inverses. It happens. So process that we learned. Set up this augmented matrix with the right side having the diagonal of 1s and 0s everywhere else. And let's start doing some transformations. I think I took the first row and multiplied by 1/4 to begin. I want to go ahead and get that 1 up there. So I got a 1, a -1/2, a 5/4, then I got a 1/4, a 0, and a 0. So far, so good. I noticed my second row is kind of nice to me. I already have a 0 and a 1 and a 0 there. Woo, I'm going to leave that alone. So I'm going to take my first row, multiply by 8, and add that to the third row. So first and second rows are going to stay the same as far as how they're written in the matrix here. Now I'm going to have 8 plus negative 8 is 0. Negative 4 plus 4 is 0. Oh, this is looking nice. Right? 8 times 5/4 is 10. Uh-oh. Plus negative 10 is 0. And then I've got what? 2 plus 0 is 2. 0 plus 0 is 0. 0 plus 1 is 1. Yeah-oh. So notice what happened in that third row. We got 3 zeros. In order for this to work, we have to have a 1 in row 3, column 3. But there is no way to get a 1 there. It's kind of like when you're solving equations and like you have 0x, 0y, 0z equals like a number, you know, that kind of situation. It's kind of like that where you stop and you go, well, this ain't happening. So this one you just say, the inverse does not exist. It's kind of like when you find out there's no solution. Not exactly the same thing, but it's that kind of thinking. So that's the example where that might that it would look like if that happened. All right. How about we get to solving some systems of equations and then call it a day. So one more little topic dealing with matrices, and that'll wrap up all your matrix stuff for now. Did you know that if you have a system of equations, you can write it up as a matrix? Let's say you have a system like, okay, so let's talk about solving systems using inverse matrices. Let's say you have a system like 5x plus 2y equals negative 1, and 2x plus 3y equals 15. You can set this up where you take the coefficients of your equations and make a matrix with those, and then multiply it with a matrix just made with the variables, and set that equal to those solutions over there. Make a matrix with those. So you can set it up so that you have a matrix A times, we'll call this matrix capital X, equals matrix B. You can set it up like that. And if you don't believe me, multiply it out. Take matrix A and multiply it with matrix X and see that that gives you 5x plus 2y and 2x plus 3y. And then we know that it equals, so that should be a multiplication sign, equals the negative 1 and the 15. It works. So that's one way to set it up. But knowing we can set it up like that, do matrix A x times matrix X equals matrix B, we can also use what we know about inverses to help us with solving. We can take both sides of this equation and multiply by the inverse of matrix A. You can do a little bit of work where, you know how you have the associative property? Well, you can associate the inverse matrix with A and leave X outside the parentheses. That's perfectly okay. But we also know that taking inverse times the matrix gives us an identity matrix. And the identity matrix times X would just leave us with matrix X. So it turns out if we want to solve to get x and y, which is in matrix X, we can take the inverse matrix of A and times it by B. And that'll get us our solutions. Cool, huh? All right, in the interest of time, in the example, I'm going to go ahead and tell you what the inverse is. I'm not going to find it for you. I'm going to tell you what it is and then show you how to use it. All right, so for matrix A, we had 5, 2, 2, 3. And I'm going to tell you that the inverse of matrix A is, it's nasty, 3/11, negative 2/11, negative 2/11, 5/11. Lovely, right? Okay, so when we had AX equals B, we had 5, 2, this is actually still carried over from the previous example if you didn't realize. We had this. So what we're going to do now is we're going to take that inverse matrix with the 3/11, the negative 2/11, negative 2/11. Why did my pen not right there? And the 5/11. And we're going to multiply that with B, the negative 1 and the 15. And see what that gets us. All right, row 1 times that column matrix. We'll have negative 3/11, negative 30/11, so that's negative 33/11, which is negative 3. Then in row 2 with that column matrix, we'll have 2/11 plus 75/11, which would be 77/11, or 7. So this gives us our solution. We know that x equals negative 3, y equals 7. Your book could say the solution set contains the ordered pair negative 3, 7. That's how your book will write it. If you go back to those equations, you can check it. You can say, well, if that's my x and y, then I should be able to plug it in and make it work. And you can. Like 5x, so 5 times negative 3, plus 2y, so 2 times 7, equals negative 1. Yep. And then 2x, so 2 times negative 3, plus 3y, or 3 times 7, so negative 6 plus 21 equals 15. Yep. Checks out. Woohoo. All right. Let's do a 3 by 3 real quick. Let's say your matrix A, you have negative 4, 2, 0. You have 1, negative 1, 2, 0, 1, 4. And then you're multiplying with x, which is xyz in this case. And then that equals b, which is 12, 7, and 20. I'm going to leave it up to you to find the inverse of A on your own, like practice finding that. I already found it, so I'm just going to go ahead and write it down to save time, because I feel like this video is already long enough. If you are not sure, if you try to do it and you can't find it, you can always message me and I'll be glad to help you out. But you should have negative 3/8, negative 1/2, 1/4, and then you should have negative 1/4, negative 1, 1/2, and you should have 1/16, 1/4, and 1/8. So you're going to take that matrix and multiply it with B. And when you do, you'll have your solution set. Just making sure I copied everything correctly before I move to the next slide. Okay, So we're going to take a inverse matrix A times B. So we're going to take -3/8, -1/2, 1/4, -1/4, -1, 1/2, 1/16, 1/4, 1/8. And we're multiplying that with the column matrix 12, 7, 20. It's going to be another column matrix. You have a 3 by 3, and you're multiplying that with a 3 by 1. So you're allowed to multiply it because the insides are the same. And then the outsides tell you it's going to be a 3 by 1 when you're done. 3 rows, 1 column. Rows come before column. RC Cola. Okay. So first row with that column, I end up with -36/8. I end up with -12/2, or I'm just going to leave it like that. And I end up with 12/4. This is -6. This is 3. All right. I messed up something. Oh, I multiplied. I used 12 again in the middle. Why did I do that? I kept using 12. Sorry. Okay, it's getting too late. Past my bedtime. -3/8 times 12. That's -36/8. -1/2 times 7 is -7/2. 1/4 times 20 is 24. That's going to be better. -7/2 is the same thing as -28/8. So that ends up being what? -64/8, or -8 plus 20/4 is 5. So you end up with -3. Much better. All right, row 2 with that column. -1/4 times 12 is -3. -1 times 7 is -7. 1/2 times 20 is 10. That ends up getting us 0. Then row 3 with that column, 12/16 plus 7/4 plus 20/8. So this is 28/16. This is 40/16 if you want to like add the fractions. 40 plus 40 is 80/16. So that reduces to 5. So there you go. So the solution set is the ordered triple, -3, 0, and 5. And if you went back to the original system of 3 equations, 3 unknowns, you could plug those in and it would work. And so if you went back to the original system, you would have, let's see, -4 times -3 is 12, plus 0 is still 12, plus 0 is still 12. Yep, it equals 12. Then you would have 1 times -3 is -3, plus 0, still -3, plus 10 is 7. Yep, that worked. Then you'd have 0 plus 0, 0, 4 times 5 is 20. Yep, that works too. So there it is. So that's how you can use the inverses to help you solve a system of equations. So solving with matrices. Yay! So much fun, isn't it? So we're using this to solve square linear systems of equations. So a square system has the same number of equations as variables. So like 3 equations, 3 unknowns. 2 equations, 2 unknowns. You could go as high as you want. 4 equations, 4 unknowns. 5 equations, 5 unknowns. Matrices are a really nice, orderly way to work with with systems with more variables. If you try to go the other route with just doing substitution, elimination, that kind of thing, a 5 by 5 system could be quite brutal. But to do it with matrices, it might not be as bad. Try it, It'll still be a lot of computation, a lot of work, but not as bad as trying to keep everything straight when you're just using substitution and elimination. So something to keep in mind as you go into higher dimensions. So much fun, isn't it? All right. Well, thank you for joining me. I'm a little sad that we're wrapping up matrices here. I do enjoy them, even if sometimes my mental math goes astray. But I look forward to joining you, though, in the next unit. Still lots more pre-calculus fun where this is coming from.